All right, my name is Justin Wilson. I'm a PhD candidate here at the University of Maryland in physics. And I'd like to thank the organizers for putting on a wonderful little SkeptiCamp. So I'm going to be talking about real fake particles. These in physics are actually called quasi-particles. They're not exactly particles, but they sort of emerge out of the system. They look really like they're particles themselves. So this is actually kind of important when you're looking at physics news items, because when you look at a physics news item, sometimes it'll be like, scientists found a whole new particle that solves all these problems in physics. And a lot of the times, unless it's like CERN and the LHC, they're actually finding a quasi-particle that's in like a crystal or something, and it looks like a fundamental particle, but it's not exactly. It's actually made up of stuff we already know. So I'm going to give some examples of that. So first, what do you think of when you think of a particle? So you might imagine, say, with the electron, a ball, a little ball with a negative charge. But then you might remember, oh wait, this is quantum mechanical, so in actuality it's everywhere. But then we scale it back a little bit, like, well, we can sort of say it's more or less right there. So it's not exactly everywhere, is it? But it looks like it's right there. So this picture is simplistic, but it's good enough to figure out what to do with electrons and everything. Now, I'm going to offer a new way to look at particles, like maybe even the electron, that depends on what happens when you look really, really close at the particle. To do that, we're going to have some ingredients. So I'm going to make what's called a condensed matter system. And really that just means that we use these ingredients. That's all it means. We have some electrons, and electrons, they have two states. These two spin states basically mean that the electron can be a bar magnet, as well as having the charge. And we also have lots of nuclei. So the details of the nuclei actually aren't important. It's mostly there to cancel out some electron charges and also to provide some stability. And we also have the electromagnetic field. So I couldn't think of a good picture for the electromagnetic field, but it's basically what happens when you have, when light charges repel, that's the electromagnetic field, when opposite charges attract, and also when you have the effect from bar magnets, how you can take magnets and they'll stick together and stuff. Like all of that is the electromagnetic field. So with these properties, this is enough to build any condensed matter system. As a matter of fact, almost all the systems I'll show you here, except for the last one, are made just with these guys here. So first, let's build a very simple crystal. So here, the circles, they're atoms, and the little squiggles, those are like springs between the atoms. But that's really the electromagnetic field that keeps the crystal together. So we want to take this crystal and create from it a new fake particle. So how do we do that? Well, let's look over here, for instance, and I'm going to take this atom that's in the middle of the circle and move it over a little bit. So when I move it over a little bit, notice what happens. That spring between those two particles over there is going to push that other particle away, and the one behind it is going to sort of be dragged forward. This will create sort of a vibration that'll propagate through the crystal. And this vibration is actually a particle of sound called a phonon, kind of like a photon. But instead of light, it's a particle of sound in a crystal. So a different way to make a phonon would be, say we look over here, and I put an extra electron on this atom right here. Well, because these are nuclei with positive charge around it, it's going to pull them in just a little bit. And so now that distorts the lattice as well and causes a whole bunch of phonons to sort of propagate throughout the crystal itself. So, and if we move the electron along, it'll move along and sort of emit phonons as it goes along. These are just the vibrations of the crystal. So, just for an example, when you go in one dimension, you can have these different vibrations of your crystal. So these different vibrations are just like light has different colors, except we can't, see sound and whatnot. We just can draw how the crystal is vibrating back and forth. So you might say, well, Justin, these are just waves. There's no particles here. Well, by quantum mechanics, you've probably heard about the wave-particle duality. Well, that sort of applies even here. Even though these aren't fundamental particles, these also have a wave-particle duality to them. And you can view them as these particles with this squiggly line here. You can see down here, if we represent the electron by this line with an arrow and the phonon by this squiggle, we sort of have an electron going along the lattice down at the bottom picture, and when it hits this atom right here, maybe it causes a little vibration that goes off in a direction, and it causes the electron to change direction and go in a different direction. So this is like phonon emissions, sort of. I should also mention that not all sound can be represented by a phonon. So like my voice coming to your ears right now is not actually sound particles, because you have to have this lattice of atoms. The air is not made of like a lattice of atoms together. It's more diffuse and flowing everywhere. And so unfortunately, you can't actually represent that with a particle. You have to be inside the crystal itself to say that it's a particle. All right, so now we want to take our ingredients and make a new particle from this. We want to actually make an anti-electron. So usually, if you have a whole bunch of energy, like at the LHC, you can just make a positron. And the positron will come and it'll collide with the electron, they'll kill each other completely. But we don't have that much energy. All we have is electrons, and we have nuclei and the electromagnetic field. So how are we going to make an anti-electron? Well, it can be done, and we're going to do that by putting a whole bunch of electrons down. We have a whole lot of them. So now let's take an electron away. So now there's a lack of an electron, or a hole right there. Well, this hole, since there's less charge there, it sort of attracts the other electrons into it from the sides, and it can sort of move around a little bit. Well, that's kind of like a particle. So let's see what happens when we add in an electron here. Well, now where this electron is, there is a lot of negative charge, and where the hole is, there's a little bit less negative charge. So actually, they'll sort of attract each other due to this like inequality in how much electric charge there is. And so if you let it go, they'll fly together, and the electron will fall into the hole and emit a phonon. So this is actually something you can represent again with a diagram. This is the electron and the hole coming together. Notice the arrow for the hole is backwards, because that is sort of the directions that electrons are flowing. So a hole sort of goes in the opposite direction that the electrons are actually moving in. And they come together, kill each other, just like a positron might, except we don't have that kind of energy, if you recall, and it emits a phonon. Well, we can also flip this diagram entirely around. So what does it mean to put a phonon into a system? Well, it might mean what you think. You just like hit it. So if we just like hit the system, it can excite an electron in a hole, an electron-hole pair, and they'll move away from each other. So this guy here, this hole, has all the properties that we might think that an antiparticle might. And in fact, when Dirac first wrote down his Dirac equation, which has positrons and electrons in it, he actually thought that maybe all of space is filled with a whole bunch of electrons, and that positrons were actually the lack of an electron. When you hit an electron out of this huge sea that's everywhere, that a positron was actually that. Turns out that that's not exactly how QED works, which explains electrons and positrons, but it works really well for systems like this, which are your common metals and the like. So now let's take these particles that we have here, the electron and the hole, and let's make an even newer, more exotic particle. So here I'm going to create for you, or do the best I can to create a Majorana fermion. So I brought back from last year my little pictures of the cat, the alive cat and the dead cat. You can think of the electron as a cat that's alive, and a hole as like a dead cat. So quickly, since this isn't a talk about like the Schrodinger cat, I'll just say that quantum mechanics has this really strange property where if you put a quantum mechanical cat in a box, it can be both alive and dead at the same time. It's not just that you don't know, it's that it actually is both alive and dead. And then when you observe it, it collapses to one or the other. So that will be important here for these particles. So we have this string of atoms. This is actually a very special string of atoms. It involves being on like a superconductor, and it's a semiconducting wire, these various properties of it. But what's important is they have these, it can either have an electron or a hole on it. And the property of this particular material, the electrons and the holes like to be close to each other. Not on top of each other, just close to each other. And so they group up. They group up like this. But notice we have an extra electron and an extra hole at the various ends of the wire. But this also is not the unique way that you can do this. You can also do it this way. So, as you might have guessed, this is what quantum mechanics says the system is in. And this extra electron and hole, this is actually the Majorana fermion. It exists at the very end of this wire. And this is just a live cat and dead cat. Like either the electron is there or there's a hole there, but actually there's both at the same time at the end of these wires. So these Majorana fermions come in pairs because, as you notice, actually the extra electron at the end of the wires is the same electron. It's just in two locations at the same time. So these always have to come in pairs. And since the holes kind of have a positive charge to them, an effective positive charge, these particles actually have zero charge because there's a hole and an electron there at the same time. They cancel each other out. So these particles can actually even be possibly used for quantum computers. People are trying to do it now. And what's really good about them for quantum computers is that, well, with the Schrodinger's cat, you open the box and the cat is either alive or dead. Here, to open the box, so to speak, it is really hard to open this box. If you hit the system, nothing happens. If you change one of the atoms out and make it something different, nothing happens. You have to really do something to the system to make this particle go away. So it's like the box is like, it's like you're welded shut and you just can't get into it. So they could be really good for quantum computers because this quantum effect sort of sticks around, like no matter what you do to it. And this is a macroscopic system, so this isn't just looking small. You're actually looking, well, when I say macroscopic, it's still you have to have a microscope and stuff, but it's not like extremely small. So these have actually very recently been observed as well, and this is an article from Science where they observe it. And this graph here is the money graph, where I circled with the red oval. That is actually the Majorana fermion. It's this little peak that you see right in the middle there. And this is at 0 voltage, and you'd expect no charge to really flow at 0 voltage, but because of these zero charge particles, you actually get a little bit of current flowing because of them. So this isn't 100%. This could be some other property that's going on. There's still other things that need to be tested to see if they are actually the Majorana fermions, but it's really hard to test that because, like I said, that box is really hard to open. So now we've built a couple of quasi-particles. Let's build one more type of quasi-particle, and that's going to be a magnetic monopole. So just with the ingredients that we had before, we have electrons, nuclei, and electromagnetic field. We're going to make, out of just that, we're going to make a monopole. So first, let me explain magnetic frustration. So these are the rules to get a low-energy magnetic state.
If you have two magnets that are next to each other but they're flipped, that's low energy. But if they're not flipped and they're the same with each other, if north is pointing up in both or south is pointing the same direction, then that's high energy. So take this triangle. Let's start by putting a magnet right there. Now, in order to get low energy, we flip a magnet and put it there. That's a low energy state. Now, there's two possibilities for the top one. We can either put a north-south magnet there. If we do, then we have a low energy state there. Excellent. But that's unfortunately high energy. But if we go over to this other one, maybe we can fix this. So we have a south-north magnet here. And unfortunately, right out of the gate, we have high energy over there. And this is low energy. In fact, there's no way to make all of these low energy. One of them will always have to be at a high energy state. And this is what we call magnetic frustration. The system really wants to go into this low energy state, but it just can't. The lattice just won't let it. So with that, let's go to just a little bit more complicated situation I won't explain in as much detail, where we have a pyramid. So this is actually what's called spin ice, where you have a little magnet at every point in this. And the magnets that I'm using are actually okay, because if you remember, the electrons have a spin, which makes them into a little dipole magnet, a little bar magnet. So actually, the rules that give you a low energy state here are as low as you can hope to get, are that you have two norths pointing in and two norths pointing out. So you see the two top ones up there, those norths are pointing in. The two bottom ones, the two norths are pointing out. So this is as low energy as you can hope to get. It's still frustrated. There are other ways that it can maneuver, other ways that it can flip this where it's still low energy. But if you flip this, now we definitely have a high energy state. There's three norths pointing in and one pointing out. This actually corresponds to a magnetic monopole. And this is the picture that explains that in more detail. If you can see, can you make out the little pyramids in that picture? Or is it too faint? Basically, the arrows, if you can't see it, are the tips of the pyramid. And each pyramid satisfies a 2-in, 2-out rule. And if you look at picture A, there's a spin in the middle that's sort of pointing in this direction. And in picture B, it flips and points in the other direction. That creates this pair of magnetic monopoles. The red one is a north, and the blue one is a south. Now, if we have a whole bunch of these pyramids and we make a big lattice of all these pyramids, we can actually move these monopoles around from each other and distance themselves away from each other. They're connected by a string that connects them, that accounts for the fact that we don't actually have magnetic monopoles, but they look really close. As a matter of fact, if you go up to the system and you measure the magnetic field, you would say, oh my God, there's a magnetic monopole here. And in fact, people have done that. So people have looked at this spin ice system, and they found these magnetic monopoles. So this is one of the examples where the news outlets actually failed, because this was in the news back in 2009 that, oh my God, we found the elusive magnetic monopole that physicists have been looking for ages. And that's not exactly true, because there is a monopole that physicists are looking for, high-energy physicists, and it would be a fundamental particle that's whizzing around the universe, perhaps, maybe. No one knows for sure. But this is made with just electrons, nuclei, and the electromagnetism, nothing else. And just with that, we've made what looks like a magnetic monopole. It behaves like a magnetic monopole and has all these interesting properties that are just really awesome. But it is not actually a fundamental particle. So, and we still don't know if the real deal exists. So those are all the particles that you can build with well, there's a lot more particles you can build with the ingredients list that I had. There's a whole lot of them. I can't go through all of them because that would take a long time. But if we discard our ingredients list and go to like something a little bit more exotic,
there's this system called string net condensate, which is no relation to string theory whatsoever, and is very much more speculative. So this theory says that you have a whole bunch of what's called string nets, like these strings that are just all throughout space. And when you have a string that's open, the ends of the strings are electrons and positrons, while the strings themselves, they create sort of a net, and when they vibrate, that's a photon. And this actually, people have mathematically shown that this gives you QED, which is basically electrons, positrons, and electrodynamics, and it gives you it with relativity and everything. So it's really awesome. And it's a shame this isn't in the popular press as much, I think, because it's a really neat idea. Now, like I said, this is not string theory, even though there are strings in it. There's no 11 dimensions. This is all still 3 dimensions and everything. It's just strings in this that look at very low energies. If you don't look hard enough, they look like electrons, positrons, and electromagnetism. So with that, I'll wrap up. These are the fake particles we discussed. We have photons, which are the vibrations of a crystal. We have holes, which are the sort of antiparticle to electrons that we can make. And we have Majorana fermions, which are these really strange quantum mechanical combinations of electrons and holes. We also have magnetic monopoles, and we have maybe electrons and photons. Now, I didn't mention in the last slide that this model that has electrons and photons, this isn't observable yet. You'd have to be able to look much closer than we're able to now. Like the LHC looks really close, but you'd have to look even closer to see if this is actually the case. So, but it's very tantalizing, and if you don't look too close, all of these look like particles. But if you start to look really close, they start to break down and not look like particles anymore, which sort of brings me to my final question. If all of these fake particles look like real particles, provided we don't look too close, what other particles that we know of are actually fake? Thank you.